The Big Bang is the most widely accepted theory of how the universe began, and it marks the birth of not just matter and energy, but space and time itself. The theory proposes that the universe started as an infinitely small, dense point about 13.8 billion years ago and has been expanding ever since. But while we understand the evolution of the universe after the Big Bang, the question remains, what caused the Big Bang? What set in motion the creation of everything we know? In this chapter, we will explore the concept of the Big Bang, the early universe, and how scientists came to understand the origins of the cosmos. We will also examine the theories and hypotheses about what could have caused the Big Bang and what the true nature of the universe's beginning might have been. As we dive into these mysteries, we'll reveal the ongoing search for the answer to one of the biggest questions in science. What happened before the Big Bang? The birth of the universe. What is the Big Bang? The term Big Bang often evokes images of an explosive event, but this is a misinterpretation. The Big Bang was not an explosion in the traditional sense. It was the beginning of space-time itself, where the entire universe began as a singularity, a point of infinite density where matter and energy were compressed into an infinitely small space. Instead of an explosion, the Big Bang represents a rapid expansion from a hot, dense state. It is often referred to as the cosmic inflationary model, where the universe underwent an exponential expansion in the first fractions of a second, growing from smaller than an atom to the size of a galaxy almost instantly. This rapid expansion is key to understanding how the universe evolved from an almost uniform, hot, and dense state to the vast, complex cosmos we observe today. In the earliest moments of the universe, everything was energy. There were no stars, galaxies, or even atoms. The first particles, quarks, electrons, and photons, formed as the universe began to cool. These particles would eventually combine to form the protons and neutrons that make up atomic nuclei. But this all began with a singularity, and the question we must now answer is, what caused this singularity to expand? Theories about what caused the Big Bang. The question of what caused the Big Bang is one of the most fundamental and challenging in cosmology. We know that the universe started from an initial, hot, dense state and expanded rapidly, but the cause of this event remains elusive. Several theories attempt to explain the origin of the Big Bang, ranging from quantum fluctuations to the idea of a multiverse. 1. Quantum fluctuations, the role of the quantum world. One of the leading theories about the cause of the Big Bang comes from the field of quantum mechanics. According to the principles of quantum theory, even empty space is not truly empty. Instead, space is filled with quantum fluctuations, tiny random changes in energy that occur constantly, even in a vacuum. These fluctuations can give rise to particles and fields from nothing. In some models of the Big Bang, the universe itself could have arisen from a quantum fluctuation. This suggests that the entire universe began as a tiny fluctuation of energy, which then expanded and evolved into the cosmos we see today. The idea is that in the quantum world, space-time can spontaneously come into existence, a concept known as quantum creation. This idea is still theoretical and remains one of the most debated topics in cosmology. 2. The multiverse theory. The universe as part of a greater whole. Another possibility is the idea that our universe is just one of many in a vast multiverse. In this theory, the Big Bang could have been triggered by the collapse of another universe or the interaction between universes. The multiverse theory suggests that our universe may not be the only one to have existed, and that there could be infinitely many other universes, each with its own set of physical laws and constants. In this scenario, the Big Bang could be seen as a natural part of a larger, cyclical process in which universes are born, evolve, and die. Some multiverse models propose that each universe could undergo its own Big Bang, with new universes continuously emerging from the cosmic vacuum. This idea raises the fascinating possibility that our universe is part of a bigger, never-ending process of creation. 3. The Big Bounce, a universe in cycles. The Big Bounce theory is another intriguing hypothesis about the origin of the universe. It suggests that the universe undergoes a never-ending cycle of expansion and contraction. In this model, the Big Bang is not the true beginning of the universe, but rather the latest phase in an ongoing cycle of cosmic birth and rebirth. According to the Big Bounce theory, the universe could have expanded from a singularity in the past, only to eventually collapse under its own gravity in a big crunch. The collapse would lead to another Big Bang, restarting the cycle. This theory would mean that the universe has gone through countless cycles of expansion and contraction, and the Big Bang we observe is just the most recent chapter in a longer cosmic history. 4. The role of inflation. A rapid expansion. While inflation does not directly explain what caused the Big Bang, it plays a crucial role in our understanding of the early universe. Inflation theory was introduced in the 1980s by physicist Alan Guth to explain the uniformity and flatness of the universe we observe today. According to this theory, the universe expanded exponentially in the first fraction of a second after the Big Bang, causing it to grow from smaller than an atom to the size of a galaxy almost instantly. Inflation theory suggests that a quantum field, often referred to as the inflaton field, caused this rapid expansion. This field could have been responsible for the release of the energy that triggered the creation of the universe, making it one of the potential explanations for what caused the Big Bang. However, the exact mechanism behind the inflaton field is still not fully understood, and the search for a better understanding of inflation continues. The role of singularity. Was the Big Bang the beginning of time? A crucial question surrounding the Big Bang is whether it marks the beginning of time. According to our current understanding of general relativity, the singularity from which the Big Bang originated represents a point where space-time itself becomes infinitely curved and the laws of physics break down. At this point, our current models cannot describe the conditions of the universe, and we have no way of knowing what happened before or at the very moment of the Big Bang. If the Big Bang marked the beginning of space-time, then time itself would have begun at that moment, making the question of what came before the Big Bang meaningless. The universe may have had no before, as the concept of time itself would not have existed prior to the Big Bang. This concept raises deep philosophical and metaphysical questions as it challenges our understanding of reality and time. What caused the Big Bang? The limits of current knowledge. Despite our best efforts, the true cause of the Big Bang remains a mystery. We have gathered substantial evidence supporting the idea that the universe began as a singularity and expanded rapidly, but the question of what set this process in motion remains unresolved. Some scientists speculate that the cause of the Big Bang could be beyond the scope of current physics, possibly requiring a new theory that combines quantum mechanics and general relativity. Furthermore, as our observational tools improve, we may uncover more clues about the origin of the universe. Experiments in particle physics, the study of gravitational waves, and the development of new technologies like the James Webb Space Telescope could provide more insights into the earliest moments of the universe and the potential causes of the Big Bang. Conclusion: the ongoing search for answers. The question of what caused the Big Bang is one of the greatest mysteries in science. While we have made significant strides in understanding the early universe, the true cause of the Big Bang remains elusive. Whether it was the result of quantum fluctuations, a multiverse, or some other unknown force, the answer to this question has profound implications for our understanding of the universe, time, and existence itself. As we continue to explore the cosmos, we may one day uncover the true origins of the universe, an answer that could reshape our understanding of reality and our place in the vast, ever-expanding cosmos. Until then, the search for the cause of the Big Bang remains one of the most exciting and fundamental quests in science. The Big Bang marks the beginning of everything we know: space, time, matter, and energy. But while we have a general understanding of the events following the Big Bang, the first moments of the universe are still shrouded in mystery. The universe's birth is believed to have begun from a singularity, a point of infinite density, and then rapidly expanded during a phase known as cosmic inflation. These early moments are key to understanding the fundamental nature of the universe, and they set the stage for everything that would come after. In this chapter, we will explore the crucial moments following the Big Bang, from the singularity to the first few fractions of a second of rapid cosmic inflation. We will also examine how inflation solves some of the biggest puzzles in cosmology and what it means for our understanding of space and time. By looking at these early stages, we can gain insight into how the universe transitioned from a hot, dense point into the vast cosmos we see today. The singularity, the beginning of space and time. To understand the Big Bang and the early moments of the universe, we must first examine the singularity, the point at which the universe began. In classical physics, a singularity is a point where the laws of physics break down and matter and energy are compressed into a state of infinite density. The singularity is thought to have contained all the mass, energy, space, and time of the entire universe in a space so small it cannot be described by conventional means. At the moment of the Big Bang, this singularity expanded rapidly. It's important to note that this wasn't an explosion in space. There was no center from which everything exploded outward. Instead, it was an expansion of space itself. The singularity represents a state of infinite density, but the precise conditions and mechanisms that caused it to expand remain one of the biggest mysteries in cosmology. The idea that the universe began from a singularity raises profound questions about the nature of time and space. According to Einstein's theory of general relativity, space-time is not fixed, but can be influenced by mass and energy. In the case of the singularity, space-time would have been compressed into a point of zero volume and infinite density, making it impossible to apply our usual understanding of physics. However, as we move beyond the singularity, the expansion begins. This rapid expansion of space-time from this state of infinite density is what we call the Big Bang. Cosmic inflation, the rapid expansion of the early universe. The next key stage in the universe's evolution is cosmic inflation, a period of exponential expansion that occurred within the first fraction of a second after the Big Bang. This theory was proposed in the 1980s by physicist Alan Guth to explain some of the universe's observed features that were difficult to account for, such as the uniformity of the universe on large scales. During cosmic inflation, the universe expanded at an incredible rate, increasing in size by a factor of at least 1026, a number with 26 zeros, in just 10^36 to 10^32 seconds. The result of this expansion was that the universe grew from an infinitesimally small point to about the size of a golf ball almost instantaneously. Inflation explains several puzzles about the early universe, including its uniformity. Without inflation, regions of the universe far apart from each other could not have interacted enough to reach the same temperature or structure. Inflation, however, caused the universe to become nearly uniform in all directions, smoothing out the irregularities that could have led to the large-scale structures of galaxies and clusters we see today. The inflaton field, the driver of cosmic inflation. At the heart of the inflationary model is the concept of the inflaton field, a hypothetical scalar field that permeated the entire universe during its rapid expansion. The energy contained in the inflaton field is thought to have driven the exponential growth of the universe. As the universe expanded during inflation, the inflaton field's energy was gradually released, and the universe transitioned into the state we observe today. The precise nature of the inflaton field remains speculative, and the field itself has not been detected directly. However, its role in shaping the universe's early evolution is key to understanding how the universe grew so rapidly from an almost incomprehensible singularity to the vast expanse of galaxies, stars, and cosmic structures. One way that inflation may have worked is through quantum fluctuations in the inflaton field. These fluctuations could have given rise to small density variations that would later develop into the galaxies and clusters we observe today. These tiny variations in density were stretched by inflation, and as the universe continued to expand, these fluctuations served as the seeds for all the large-scale structure of the universe. The formation of the first particles. Matter emerges. After the inflationary phase ended, the universe began to cool rapidly. As the temperature dropped, particles began to form. The first fundamental particles, quarks, electrons, and neutrinos, came into existence from the energy released during inflation. Quarks are the building blocks of protons and neutrons, and these particles were the precursors to the atomic nuclei that would eventually form. During the early universe, particles like quarks and gluons, which mediate the strong force, existed in a state of quark-gluon plasma, a high-energy soup in which quarks and gluons were free to move independently. As the universe cooled, quarks began to combine into protons and neutrons, which in turn formed the building blocks of atoms. At this stage, the universe was a hot, dense plasma, and it was still too hot for atoms to form. The early universe was dominated by energy, but as it expanded and cooled, matter began to take form. This process continued for the first few minutes after the Big Bang, eventually leading to the formation of the first atomic nuclei, including hydrogen, helium, and traces of lithium. The cosmic microwave background, CMB, a snapshot of the early universe. The formation of atoms occurred about 380,000 years after the Big Bang during a process called recombination. Prior to this, the universe was filled with a dense ionized gas of protons, electrons, and photons, which constantly scattered light and prevented photons from traveling freely. Once the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, the photons could travel freely through space, creating the cosmic microwave background, CMB. The CMB is the oldest light in the universe, and it provides a snapshot of the universe when it was just a few 100,000 years old. The CMB shows the temperature fluctuations in the early universe, which are the seeds from which galaxies, stars, and other cosmic structures would eventually form. These tiny fluctuations provide a wealth of information about the universe's early state, and by studying them, scientists can learn about the conditions that existed right after the Big Bang. The Big Bang nucleosynthesis, the formation of the first elements. In addition to the formation of particles like quarks and electrons, the first few minutes of the universe also saw the creation of the light elements. During a process called Big Bang nucleosynthesis, protons and neutrons fused to form the first atomic nuclei, such as hydrogen, helium, and small amounts of lithium. These light elements are the building blocks for the more complex matter we see in the universe today. This period of nucleosynthesis happened very quickly, within the first 3 minutes of the universe's existence. The exact amount of each element formed during this period is consistent with what we observe today in the universe, and the study of these elements provides strong evidence for the Big Bang theory. The challenges of understanding the Big Bang. What came before? One of the most intriguing questions surrounding the Big Bang is, what came before the Big Bang? According to current models of cosmology, the Big Bang marks the beginning of time itself, meaning that time and space as we know them were created at that moment. The Big Bang is not an event that happened in space, but rather it represents the creation of space. As such, asking what happened before the Big Bang might not be meaningful, since time itself did not exist prior to the Big Bang. Nevertheless, theories such as the multiverse and cyclic models suggest that the Big Bang could have been part of a larger eternal cycle of cosmic births and deaths. These ideas propose that the universe may not have had a true beginning, and that the Big Bang could be just one event in an infinite series of cosmic creations and collapses. Conclusion: the mystery of the Big Bang's cause. The Big Bang represents the birth of everything we know: time, space, matter, and energy. While we have a relatively good understanding of how the universe evolved after the Big Bang, the question of what caused it remains one of the greatest mysteries in cosmology. Several theories, such as quantum fluctuations, the multiverse, and cosmic inflation, provide possible explanations, but the true cause of the Big Bang is still unknown. As our understanding of physics deepens and as we continue to observe the cosmos, we may one day uncover the true origins of the universe. Until then, the Big Bang remains one of the most profound and fundamental concepts in science, shaping our understanding of the universe and our place within it. The theory of cosmic inflation is one of the most important ideas in modern cosmology, providing a crucial explanation for the early universe's rapid expansion and the uniformity of the cosmos. Proposed by physicist Alan Guth in the early 1980s, inflation posits that the universe underwent a period of exponential expansion during the first fraction of a second after the Big Bang. This expansion was so rapid and intense that it stretched space-time, smoothing out irregularities and setting the stage for the universe's large-scale structure. In this chapter, we will explore the concept of cosmic inflation in detail. We will examine how this theory helps explain the homogeneity and isotropy of the universe, solve problems in Big Bang nucleosynthesis, and offer insights into the formation of galaxies, stars, and other structures. Inflation has reshaped our understanding of the very early universe, but questions still remain about the nature of the inflaton field, the mysterious force that drove this exponential expansion. The basics of cosmic inflation. Cosmic inflation refers to a rapid expansion of spacetime that occurred during the first 10^36 to 10^32 seconds after the Big Bang. According to this theory, the universe expanded from a tiny point, much smaller than an atom, to approximately the size of a galaxy in a fraction of a second. This expansion happened faster than the speed of light, which might seem impossible under normal physics, but it is consistent with general relativity. The idea behind inflation is that the universe's vacuum energy, the energy inherent in empty space, caused space to stretch incredibly quickly. During this brief period, the universe grew by a factor of 10 to 26, a number with 26 zeros, in a fraction of a second. This exponential expansion solved many of the puzzles that arose in the early Big Bang models, such as the horizon problem, the flatness problem, and the monopole problem. Solving the horizon problem, uniformity of the universe. One of the biggest puzzles in cosmology before the introduction of inflation was the horizon problem. This refers to the uniformity of the universe on large scales. The universe is remarkably homogeneous and isotropic, meaning that it appears largely the same in every direction, with only slight temperature fluctuations in the cosmic microwave background, CMB. The problem is that regions of the universe that are now extremely far apart have not had enough time to exchange information or energy with one another. According to traditional Big Bang theory, there shouldn't be enough time for these distant regions to come into thermal equilibrium. However, inflation solves this problem by proposing that, before the universe expanded exponentially, all regions of the cosmos were close together and in thermal equilibrium. During the brief period of inflation, the universe's rapid expansion stretched space-time to such an extent that distant regions that are now far apart were once in contact, allowing them to achieve the same temperature and energy distribution. Inflation effectively solves the horizon problem, explaining why the universe looks so uniform and why the CMB radiation is the same temperature in all directions. The flatness problem. Why the universe is so close to flat. Another problem that inflation addresses is the flatness problem, which concerns the shape of the universe. In general relativity, the geometry of the universe is influenced by its total mass and energy. If the density of the universe were too high, spacetime would be curved inward, while if the density were too low, spacetime would be curved outward. The critical density of the universe is the exact amount that would keep the universe flat, and before inflation, models suggested that the universe's density was either much higher or much lower than the critical value. However, inflation proposes that during the exponential expansion, the universe was stretched to such a degree that it became extremely flat. After inflation, the universe was so close to the critical density that it appears to be flat on large scales, as we observe today. This theory elegantly resolves the flatness problem by suggesting that inflation stretched the early universe so much that its curvature became negligible. The monopole problem. Absence of magnetic monopoles. Another mystery in early cosmology was the monopole problem, which referred to the theoretical prediction of magnetic monopoles. Particles with only one magnetic pole, either north or south, unlike the dipoles we observe in nature, e.g., a bar magnet with both a north and south pole. In many grand unified theories, GUTs, such as those that try to unite the four fundamental forces of nature, magnetic monopoles were predicted to be produced in large numbers during the early universe. However, when scientists searched the universe, they found no evidence of magnetic monopoles, suggesting that they either didn't exist or their abundance was much lower than expected. Inflation provides a solution to this problem by suggesting that the rapid expansion of the universe diluted any magnetic monopoles that may have existed, reducing their number to levels so small that they are undetectable. The inflated field. What drove inflation? While inflation solves several critical problems in cosmology, one of the biggest mysteries remains. What caused inflation? The answer lies in the concept of the inflated field, a hypothetical quantum field thought to have driven the universe's rapid expansion. The inflated field is believed to have been a form of vacuum energy that existed throughout the universe, causing spacetime to expand exponentially. As the inflated field decayed, its energy was released, fueling inflation and leading to the creation of particles and fields that would later form the universe's galaxies, stars, and matter. The exact nature of the inflated field is still unknown, and many different models have been proposed. The field could have been a type of scalar field, similar to the Higgs field, which is responsible for giving particles mass. The inflated field's energy is believed to have decayed into the particles and radiation that populated the universe, kickstarting the Big Bang's subsequent evolution. Despite the progress in understanding inflation, we have not yet directly detected the inflated field. Observing its effects could be the key to understanding the true cause of cosmic inflation, and scientists are searching for clues in a variety of ways, including through cosmic microwave background measurements and particle physics experiments. Inflation and the formation of large-scale structure. One of the most significant consequences of inflation is the creation of tiny quantum fluctuations in the inflated field. These fluctuations were stretched during inflation and became the seeds for the formation of the universe's large-scale structures. These early density fluctuations in the fabric of space-time are the origins of galaxies, clusters, and cosmic voids. After inflation ended, these small fluctuations in density began to collapse under gravity, forming the first stars, galaxies, and superclusters. This process continues today, as gravity pulls together gas and dust to form new stars and galaxies. The study of these fluctuations in the cosmic microwave background, CMB radiation, allows scientists to trace the origins of structure in the universe and understand the process by which the cosmos became the complex interconnected system we observe today. Testing inflation, the search for evidence. While inflation is a widely accepted theory, it remains a hypothesis, and much work is still needed to test its predictions. One of the most important avenues for testing inflation is the study of the cosmic microwave background, CMB. Tiny temperature fluctuations in the CMB, which were created during inflation, contain valuable information about the inflationary period and can help scientists learn more about the inflated field and the early universe. Another key test for inflation comes from gravitational waves, ripples in spacetime caused by the acceleration of massive objects. Inflation may have created primordial gravitational waves in the early universe, and detecting these waves would provide direct evidence for inflation and the quantum fluctuations that drove the expansion. Several upcoming experiments, such as the James Webb Space Telescope and LIGO, aim to measure these waves and provide further confirmation of inflation. Conclusion: inflation and the origins of the universe. Cosmic inflation is one of the most profound and successful ideas in modern cosmology. It offers elegant solutions to several key puzzles about the early universe, such as the uniformity of the cosmos, the flatness of space, and the absence of magnetic monopoles. Inflation also provides a framework for understanding the large-scale structure of the universe and the formation of galaxies and stars. While the inflaton field itself remains a mystery, inflation provides a crucial piece of the puzzle in our quest to understand the origins of the universe. As we continue to study the early universe and the cosmic fluctuations left behind by inflation, we may one day uncover the true nature of the forces that shaped our universe and set it on its current path. After the Big Bang, the early universe was an incredibly hot and dense place, where all of the matter and energy of the cosmos existed in a primeval soup. As the universe expanded rapidly during the period of cosmic inflation, it began to cool, setting the stage for the formation of particles and elements that would eventually lead to the creation of the stars, galaxies, and planets we see today. But the first few minutes after the Big Bang were crucial for the creation of matter, and understanding these moments is key to comprehending the evolution of the universe. In this chapter, we will explore the first moments of the universe's existence, starting with the formation of the fundamental particles, quarks, electrons, and neutrinos that make up the building blocks of all matter. We will also examine the processes of nucleosynthesis, where the first atomic nuclei formed, and how these early elements laid the foundation for everything that followed. From the creation of the first particles to the formation of atoms, the first few minutes were critical in shaping the universe as we know it. The formation of the fundamental particles. In the immediate aftermath of the Big Bang, the universe was a hot, dense plasma of quarks, gluons, electrons, and photons. These particles were in a state of constant interaction, and the universe was too hot for anything to form beyond the most basic particles. The temperature was trillions of degrees Celsius, so high that atomic nuclei could not hold together. Quarks are the fundamental building blocks of matter and combine to form protons and neutrons. Gluons are the particles that carry the strong nuclear force which binds quarks together. In the first moments of the universe, quarks and gluons existed freely in a hot, dense state known as the quark-gluon plasma. As the universe expanded and cooled, quarks began to combine into protons, positively charged, and neutrons, neutral, forming the building blocks of atomic nuclei. Electrons, which are negatively charged particles, also began to form. But at this stage, they existed independently of atomic nuclei because the universe was still too hot for electrons to combine with protons to form neutral atoms. The formation of the first atomic nuclei, Big Bang nucleosynthesis. A few minutes after the Big Bang, the universe had cooled enough for protons and neutrons to begin combining through nuclear reactions, forming the first atomic nuclei. This process is known as Big Bang nucleosynthesis. During the first few minutes, hydrogen, helium, and small amounts of lithium were created in a highly energetic, rapid process. The most abundant element produced during this period was hydrogen, in the form of protium, which consists of a single proton, making up about 75% of the mass of ordinary matter in the universe. The second most abundant element was helium, specifically the helium-4 isotope, which was formed through the fusion of protons and neutrons. The production of helium during this period was incredibly important as it laid the groundwork for the formation of stars and galaxies later on. A small amount of lithium was also produced in these first few minutes. The process of nucleosynthesis continued for about 20 minutes, after which the universe had cooled sufficiently that the creation of new nuclei ceased, leaving behind a universe dominated by hydrogen, helium, and traces of lithium. The cooling and formation of neutral atoms. After about 380,000 years, the universe had cooled sufficiently for electrons to combine with protons to form neutral hydrogen atoms. This process is called recombination. At this point, the universe became transparent to light, allowing photons to travel freely through space. This was a crucial turning point as it marked the decoupling of matter and radiation. Before this, the universe was opaque, with photons constantly scattering off free electrons. The formation of neutral atoms was critical for the evolution of the universe. Before this, the universe was filled with an ionized gas, a plasma, and light was scattered by free electrons. When neutral hydrogen atoms formed, light could travel freely through space for the first time, marking the birth of the cosmic microwave background, CMB radiation. The CMB is the afterglow of the Big Bang and provides a snapshot of the universe at the time of recombination, revealing crucial information about the state of the universe at that early stage. The cooling of the universe also allowed for the formation of neutral helium atoms, which would play a role in the formation of early stars and galaxies. However, it would take hundreds of millions of years before the first stars were born. The cosmic microwave background, a snapshot of the early universe. The cosmic microwave background, CMB, is a key piece of evidence supporting the Big Bang theory and offers a glimpse into the early universe, when it was just 380,000 years old. The CMB is the remnant radiation from the hot plasma that filled the universe during its early stages. As the universe cooled and matter became neutral, photons were no longer scattered by free electrons and could travel freely through space. These photons make up the CMB we observe today. The CMB provides a wealth of information about the early universe. By studying its temperature fluctuations, scientists can learn about the density variations in the early universe, which eventually grew into the galaxies and clusters of galaxies we see today. The CMB is incredibly uniform, but it contains tiny fluctuations, about 1 part in 100,000, which represent the seeds from which galaxies and large-scale structures formed. The role of matter and radiation. In the early universe, matter and radiation were tightly coupled. The high temperatures meant that photons, light particles, were constantly scattering off free electrons, preventing the universe from being transparent. As the universe cooled, matter began to form more stable structures. However, these early structures were still in a highly energetic state, and the universe was filled with radiation in the form of high-energy photons. Over time, the universe's expansion caused it to cool, and the amount of radiation relative to matter decreased. This shift in the balance between matter and radiation has had a profound impact on the universe's evolution. The early universe was dominated by radiation, in the form of photons, but as it cooled, matter, in the form of hydrogen, helium, and other elements, took over, leading to the formation of the first galaxies, stars, and planets. The first stars and galaxies, the next steps in evolution. While the universe had cooled enough to form neutral atoms after recombination, it would take millions of years before the first stars began to form. These first stars were formed from the hydrogen and helium produced in the Big Bang, and they would eventually ignite through nuclear fusion, creating light and heat for the first time in the history of the universe. As these stars formed, they began to combine atoms into heavier elements through the process of stellar nucleosynthesis. These heavier elements, such as carbon, oxygen, and iron, were essential for the formation of future generations of stars, planets, and even life. The first stars, known as population 3 stars, were likely much more massive and short-lived than the stars we see today, but their deaths in supernova explosions seeded the universe with the elements that would go on to form galaxies, planets, and eventually life. Conclusion: the first moments of the universe, from energy to matter, the first few minutes and even the first few seconds of the universe's existence were crucial for setting the stage for everything that came after. From the formation of fundamental particles like quarks and electrons to the creation of the first atomic nuclei and atoms, these early moments were a period of rapid transformation. As the universe cooled, matter began to form, and light could finally travel freely, creating the cosmic microwave background that provides a snapshot of the early universe. Through processes like Big Bang nucleosynthesis, the universe was seeded with the elements that would later form the stars, galaxies, and planets we see today. Although the universe was initially a hot, dense soup of energy, the transition from this state to a more structured universe filled with matter was a key part of the cosmic evolution. In the next chapter, we will delve deeper into the formation of the first stars and galaxies, and how the early universe began to develop the complex structures that would eventually lead to the formation of the cosmos as we know it. After the Big Bang and the first few minutes of the universe's existence, where the foundation for matter and energy was laid, the universe began its long and slow journey toward the formation of cosmic structures. The first stars and galaxies played a pivotal role in shaping the universe, providing the light and elements needed for the evolution of complex structures like planets and eventually life. Understanding how stars and galaxies formed is key to understanding the development of the universe and the role that gravity, radiation, and dark matter played in this process. In this chapter, we will explore how the first stars came into existence, what conditions were required for their formation, and how gravity and dark matter played central roles in the development of the first galaxies. We will also delve into the chemical evolution of the universe, looking at how the first stars created the heavy elements that would go on to form planets, and eventually the building blocks for life. The formation of the first stars, from gas to fusion. After the universe cooled sufficiently and the first atoms, primarily hydrogen and helium, formed, the universe was mostly filled with neutral hydrogen gas. This gas, although relatively cool compared to the early universe's extremely hot plasma, still existed in vast clouds spread throughout the cosmos. These gas clouds, or molecular clouds, would become the birthplaces of the first stars. The formation of stars began with the force of gravity pulling hydrogen gas together into denser clumps. These clumps of gas began to collapse under their own weight, and as they collapsed, they heated up. As the gas continued to collapse and its density increased, the temperature within the core of these clumps rose rapidly. At a certain point, when the core temperature reached around 10 million degrees Celsius, nuclear fusion could occur, and the first progenitors of stars were born. These early stars, known as population 3 stars, were vastly different from the stars we see today. They were massive and incredibly hot, burning through their fuel at an astonishing rate. These stars had much shorter lifespans than modern stars, likely only a few million years, because their massive size meant they consumed their fuel much more quickly. Once these stars exhausted their fuel, they exploded in massive supernovae, seeding the universe with heavier elements. The role of dark matter in star and galaxy formation. While gravity played a central role in the formation of stars, dark matter, the invisible, non-interacting substance that makes up a significant portion of the universe, also played a key role in the process. Dark matter doesn't interact with light, but it has mass and exerts a gravitational pull. Because of its gravitational influence, dark matter created halos around regions where ordinary matter, such as hydrogen gas, was accumulating. These dark matter halos provided the necessary gravitational pull to help collapse the gas into denser regions. Without dark matter, the gas clouds would not have had enough mass to collapse and form stars efficiently. Essentially, dark matter acted as a scaffolding for the formation of stars and galaxies, providing the necessary mass for gravitational collapse to occur. The first galaxies were likely born in regions where dark matter was most concentrated, and over time, these regions became the cosmic birthplaces for the first stars. The formation of galaxies, gravitational clumping, and galactic mergers. The birth of the first stars was not an isolated event. As gas clumped together to form individual stars, these clumps of matter eventually formed larger structures, galaxies. A galaxy is essentially a collection of stars, gas, and dust bound together by gravity. The first galaxies likely formed from the gravitational collapse of gas-rich regions of the universe, where dark matter acted as a guiding force, pulling together gas, dust, and stars. The formation of the first galaxies was a gradual process. In the early universe, small clumps of matter, containing stars, gas, and dark matter, began to merge together to form larger structures. Over time, these galaxies merged with others, forming galaxy clusters, vast groups of galaxies bound together by gravity. As galaxies formed and evolved, their internal dynamics began to shape their structure. Spiral galaxies, like our own Milky Way, formed as matter continued to collapse inward, forming a rotating disk. In contrast, elliptical galaxies formed from galaxy mergers, resulting in more spherical shapes with less star formation. The birth of heavy elements, stellar nucleosynthesis. As the first stars lived and died, They created and spread heavy elements throughout the universe. Stellar nucleosynthesis is the process by which stars fuse lighter elements, like hydrogen, into heavier elements, such as carbon, oxygen, and iron, through nuclear fusion in their cores. When a star dies, particularly in a supernova explosion, these heavy elements are released into the surrounding space. The explosion of massive stars during supernovae was not only a dramatic end to the lives of these stars, but also a cosmic event that seeded the universe with the raw materials needed to form planets, other stars, and eventually life. Without the creation of these elements in the cores of stars and their distribution throughout the universe, life as we know it would not be possible. Elements like carbon, nitrogen, and oxygen, key ingredients for life, were created in the hearts of stars and dispersed through space during supernova explosions. The process of stellar nucleosynthesis began with the first stars, and over time, the universe became enriched with heavier and heavier elements. These elements eventually formed the molecular clouds from which later generations of stars and planets would form. The emergence of galaxy clusters. The universe as a web. As individual galaxies continued to form, they began to interact with one another, leading to the creation of galaxy clusters. These clusters are vast collections of galaxies bound together by gravity, containing hundreds or even thousands of galaxies. The formation of galaxy clusters played a significant role in shaping the large-scale structure of the universe. Over billions of years, galaxies within these clusters have collided, merged, and exchanged gas, leading to the formation of larger and more complex structures. The interaction between galaxies within clusters also contributes to the ongoing process of galaxy evolution. While the formation of galaxies and their mergers may seem like a slow and gradual process, these interactions have led to the creation of some of the most massive structures in the universe. Clusters of galaxies are the largest known gravitationally bound structures in the cosmos, and they provide crucial information about the history and evolution of the universe. The Dark Ages, before stars and galaxies. Following the formation of the first stars, the universe entered a period known as the Cosmic Dark Ages, during which there were no new sources of light. This period lasted from about 300,000 years after the Big Bang, when the first atoms formed, to about 400 million years after the Big Bang, when the first stars began to shine. During the Dark Ages, the universe was filled with neutral hydrogen gas, and there were no stars or galaxies to emit light. Over time, the gravitational collapse of gas in the universe led to the formation of the first stars and galaxies, marking the end of the Dark Ages and the birth of the first light. The first light. The epoch of reionization. The birth of the first stars also marked the beginning of the epoch of reionization, a period in the universe's history when the first stars and galaxies emitted ultraviolet light that ionized the hydrogen gas in the cosmos. This process of reionization began about 400 million years after the Big Bang and ended around 1 billion years after the Big Bang. During reionization, the universe transitioned from being opaque to transparent, as the ultraviolet radiation from the first stars broke apart the neutral hydrogen atoms. This allowed light to travel freely through space, and the universe began to evolve into the structure we observe today. The process of reionization not only shaped the evolution of the universe, but also created the conditions necessary for galaxies and stars to form and thrive. Conclusion: the dawn of the universe, stars, galaxies, and structure. The formation of the first stars and galaxies marked the beginning of a new era in the universe. The birth of matter, the creation of heavy elements, and the gravitational clumping of matter into stars and galaxies were all essential steps in the evolution of the cosmos. These processes set the stage for the formation of planets, the development of complex structures, and the emergence of life. As the universe continued to evolve, the first stars and galaxies paved the way for the vast cosmic web of galaxies and galaxy clusters we observe today. The forces of gravity, dark matter, and radiation continue to shape the universe, and the formation of stars and galaxies remains a key part of the ongoing cosmic journey. As the first stars formed and began to shine, the universe underwent one of its most significant transformations, an event known as reionization. This period, which occurred roughly 400 million years after the Big Bang, marked the moment when the first stars and galaxies emitted powerful ultraviolet light, reionizing the hydrogen gas that filled the universe and bringing an end to the cosmic dark ages. This crucial period not only allowed for the development of the structures we see today, but also fundamentally changed the nature of the universe. In this chapter, we will explore the epoch of reionization, the processes that led to it, and its profound implications for the development of the universe. We will examine how the first stars, galaxies, and supermassive black holes played pivotal roles in this transformative period, and how the effects of reionization can still be observed today in the cosmic microwave background and the large-scale structure of the universe. What is reionization? Reionization refers to the process by which the neutral hydrogen atoms that filled the universe after the Big Bang were ionized, split into free protons and electrons by the intense radiation emitted by the first stars and galaxies. This transformation was crucial for the universe's evolution because, prior to reionization, the universe was opaque to light. The neutral hydrogen gas scattered light from stars, preventing it from traveling freely across vast distances. During the cosmic dark ages, which spanned from roughly 380,000 years to 400 million years after the Big Bang, the universe was devoid of any significant sources of light, with the only particles present being neutral hydrogen and helium. As the first stars began to shine, their ultraviolet radiation began to ionize the surrounding hydrogen gas, making it transparent to light and allowing photons to travel freely across space. This marked the end of the Dark Ages and the dawn of the cosmic age of light. The first sources of light. The birth of the first stars. The process of reionization began with the formation of the first stars, often referred to as population 3 stars. These stars were massive, hot, and short-lived, burning through their fuel much faster than the stars we see today. They were composed almost entirely of hydrogen and helium, with no heavier elements like carbon or oxygen. These stars played a crucial role in the process of reionization by emitting large amounts of ultraviolet radiation, which began to ionize the hydrogen gas surrounding them. As these early stars formed, they heated the surrounding gas, causing it to glow and scatter radiation. The photons from these first stars began to ionize the hydrogen atoms, turning the gas from neutral into a plasma of free protons and electrons. This ionization process gradually spread across the universe, slowly clearing the gas of its opacity and allowing light to travel freely once again. This marked the end of the cosmic dark ages, and the universe began to glow in the light of its first stars. The role of galaxies in reionization. While the first stars were crucial in initiating the process of reionization, galaxies played an even larger role in the full ionization of the universe. Galaxies are composed of stars, gas, and dust, and the energy produced by the stars within galaxies contributed significantly to the ionization of hydrogen gas. The intense radiation emitted by the first galaxies was capable of ionizing vast amounts of hydrogen over large regions, creating the first cosmic bubbles of ionized gas. The formation of the first galaxies also marked the beginning of galactic mergers, the process by which galaxies collide and combine to form larger structures. These mergers were essential for the growth of galaxies and the development of large-scale cosmic structures. The radiation produced during these collisions and the subsequent formation of new stars within the merging galaxies further accelerated the process of reionization. As the universe aged, galaxy clusters began to form, and these clusters acted as gravitational lenses, magnifying the radiation emitted by galaxies and stars within them. This amplification helped spread the ionizing radiation to even more distant regions, speeding up the process of reionization. The first supermassive black holes and quasars. The formation of supermassive black holes in the centers of galaxies also played a significant role in the epoch of reionization. These black holes grew rapidly by accreting gas and dust, forming some of the first quasars, extremely bright, high-energy objects powered by the infall of material into supermassive black holes. Quasars emit enormous amounts of ultraviolet and X-ray radiation, which contributed to the reionization process by ionizing the hydrogen gas in their surroundings. The radiation from quasars was particularly effective at ionizing hydrogen in the distant reaches of the universe, where stars and galaxies were too far apart to influence the gas directly. These powerful cosmic engines accelerated the process of reionization, allowing the universe to transition from a cold, dark state into a more structured and light-filled cosmos. The timeline of reionization. When did it happen? The process of reionization is thought to have begun around 400 million years after the Big Bang and continued for several hundred million years. This means that the universe was not fully ionized until around 1 billion years after the Big Bang. The exact timing of reionization is still a subject of ongoing research, but recent observations have provided important clues. One of the most valuable tools for studying reionization is the cosmic microwave background, CMB radiation. The CMB is a faint glow left over from the Big Bang and provides a snapshot of the universe when it was only 380,000 years old. By comparing the CMB with more recent observations, scientists can measure the effects of reionization on the early universe and estimate its timing. Additionally, astronomers are using observations of distant galaxies and quasars to probe the state of the universe during reionization. The Lyman alpha forest, a series of absorption lines in the spectra of distant quasars, can be used to detect the ionization state of hydrogen at various points in the universe's history. These observations suggest that reionization likely ended around 1 billion years after the Big Bang, with most of the universe becoming transparent to ultraviolet radiation by that time. The end of the Dark Ages. The dawn of a new universe. Reionization was a pivotal moment in the history of the universe, marking the end of the cosmic dark ages and the beginning of the cosmic age of light. The intense radiation emitted by the first stars, galaxies, and quasars ionized the hydrogen gas that filled the universe, making it transparent to light and allowing photons to travel freely. This transition allowed the universe to evolve from a dark, featureless space into a bright and complex cosmos filled with stars, galaxies, and large-scale structures. The epoch of reionization also set the stage for the formation of galaxies, stars, and planets, as the cleared hydrogen gas allowed matter to collapse under gravity, leading to the formation of the first stars and galaxies. Without reionization, the universe would have remained a cold, dark, and opaque place, with no possibility for the structures we observe today. The lasting effects of reionization. Reionization had lasting effects on the universe's structure. The energy released during this period heated the intergalactic medium, the gas between galaxies, and led to the formation of cosmic bubbles of ionized gas. These bubbles merged over time to form a more uniform distribution of ionized hydrogen, allowing for the development of large-scale cosmic structures like galaxy clusters. The study of reionization also provides important insights into the early universe. By examining the light from distant quasars and galaxies, astronomers can learn about the density and distribution of matter in the early universe, as well as the properties of the first stars and supermassive black holes. The ongoing study of reionization is helping us understand the origin of the universe's large-scale structure and the forces that drove the universe's evolution. Conclusion: reionization and the evolution of the universe. The epoch of reionization was a critical moment in the history of the universe. It marked the end of the cosmic dark ages, allowed for the formation of stars and galaxies, and laid the groundwork for the universe's large-scale structure. During this time, the first stars, galaxies, and quasars emitted intense radiation that ionized the hydrogen gas, transforming the universe from an opaque, featureless space into a bright, complex cosmos. Reionization is also crucial for understanding the origin of the cosmic microwave background, CMB, the formation of galaxies, and the evolution of large-scale structures. As we continue to study the effects of reionization, we are uncovering new insights into the early universe and the forces that shaped its evolution. The epic of reionization is a reminder of how far we have come in our understanding of the cosmos. It also highlights how much we still have to learn about the universe's earliest moments. The light from the first stars and galaxies, once scattered and hidden, now shines as a beacon, guiding our understanding of the universe's complex history. After the epoch of reionization, the universe entered a new era, a time when the first galaxies began to form and the structures that make up the large-scale cosmic web began to take shape. Galaxies are the fundamental building blocks of the universe, where stars, gas, dust, and dark matter come together under gravity to create vast, complex systems. Understanding how galaxies form and evolve is crucial to understanding the evolution of the universe itself. In this chapter, we will explore how the first galaxies formed, the forces that drove their evolution, and the role they played in shaping the cosmos. We will also examine the process of galaxy mergers, which played a central role in the growth of galaxies and the formation of large-scale cosmic structures. The formation of the first galaxies. The formation of the first galaxies is closely tied to the evolution of the early universe. After the epoch of reionization, the universe was filled with hydrogen and helium gas, and the first stars had begun to shine. These stars emitted radiation that ionized the surrounding gas, allowing the universe to transition from a dark, featureless place into a more complex environment. However, for galaxies to form, the hydrogen and helium gas needed to collapse under its own gravity, creating denser regions where stars could form. The first galaxies likely formed around 400 million to 500 million years after the Big Bang. These early galaxies were small, irregular, and formed primarily from hydrogen and helium. Over time, gravity caused these gas clouds to collapse, triggering the formation of the first stars. As stars formed, they began to emit light and heat, transforming their surroundings and creating stellar nurseries, regions where new stars were born. The first galaxies were probably dominated by massive, short-lived stars that burned through their fuel quickly and exploded as supernovae. These supernova explosions enriched the surrounding gas with heavier elements such as carbon, oxygen, and iron, which would later go on to form the next generation of stars and planets. The birth and death of stars played a central role in the development of galaxies and their overall chemical evolution. The role of dark matter in galaxy formation. Dark matter played a crucial role in the formation of galaxies. Although it does not interact with light and is invisible to telescopes, dark matter has mass and exerts a gravitational pull. In the early universe, dark matter began to clump together under its own gravity, forming halos around regions of ordinary matter. These dark matter halos acted as the scaffolding for galaxy formation, providing the necessary gravitational force to pull gas and dust together and form stars. Without dark matter, the gas in the early universe would not have had enough mass to collapse and form stars and galaxies efficiently. The gravitational influence of dark matter was essential for creating the dense regions where galaxies could form. Over time, galaxies grew by accreting more gas, merging with other galaxies, and forming more complex structures. Galaxy mergers, the growth of cosmic structures. As galaxies began to form, they did not remain isolated. Instead, they began to interact and merge with one another. Galaxy mergers are a natural part of galaxy evolution and have played a significant role in the growth and development of galaxies over time. The first galaxies were relatively small, but as they merged, they grew larger and more complex. These mergers were driven by gravity, which caused galaxies to attract each other and eventually collide. When two galaxies collide, their gas, stars, and dark matter interact, triggering the formation of new stars and creating complex structures like elliptical galaxies and supermassive black holes at their centers. One of the most significant consequences of galaxy mergers is the formation of supermassive black holes. These black holes are thought to reside at the centers of most large galaxies, including our own Milky Way. The growth of supermassive black holes is closely tied to the merger process, as the collision of galaxies funnels gas toward the center, where it can be accreted by the black hole. The cosmic web, large scale, structure formation. As galaxies formed and evolved, they began to cluster together in regions of space, forming the large-scale structure of the universe. The cosmic web is a vast network of galaxies, galaxy clusters, and dark matter that forms the largest structures in the universe. This web is made up of galaxy filaments, superclusters, and voids, vast empty regions of space where few galaxies exist. The cosmic web was formed through the influence of gravity, which caused matter to clump together over time. Dark matter played a central role in this process, as it acted as a scaffolding that guided the formation of galaxy clusters and superclusters. The expansion of the universe also played a role in the formation of the cosmic web, as galaxies were pulled into filaments of matter and separated by vast voids. The study of the cosmic web provides important insights into the large-scale structure of the universe and how galaxies and galaxy clusters formed over billions of years. Observations of the cosmic web also help scientists understand the role of dark matter and dark energy in shaping the universe's structure. Galaxy evolution, from irregular to spirals and ellipticals. As galaxies continued to evolve, they underwent significant changes in their structure. The early galaxies were likely irregular in shape, with no clear structure. Over time, galaxies began to develop more defined shapes, such as spiral or elliptical forms. Spiral galaxies, like our Milky Way, are characterized by their flat rotating disks and spiral arms. These galaxies are rich in gas and dust, which allows for the formation of new stars. The stars in spiral galaxies are relatively young, and the gas in the disk continues to fuel star formation. The supermassive black hole at the center of spiral galaxies plays a crucial role in the galaxy's evolution, as it helps regulate the flow of gas and star formation. Elliptical galaxies, on the other hand, are more spherical in shape and contain older stars. These galaxies have little to no gas, and star formation has largely ceased. Elliptical galaxies form primarily through the merging of other galaxies, which disrupts the gas and stars in the galaxies and causes them to settle into a more spherical shape. These galaxies are often found at the centers of galaxy clusters, where gravitational interactions are strongest. The formation of supermassive black holes. At the centers of most galaxies lies a supermassive black hole, an object with a mass millions to billions of times that of the Sun. The formation of these black holes is still not fully understood, but their creation is believed to be closely tied to the process of galaxy mergers. When two galaxies collide, the gas and stars in the center of the galaxies are funneled toward the center, where they are accreted by the supermassive black hole. As matter falls into the black hole, it heats up and emits intense radiation, often forming a quasar. These quasars can outshine entire galaxies, emitting vast amounts of light and energy. Over time, supermassive black holes grow, and their presence influences the evolution of their host galaxies. Some theories suggest that the growth of supermassive black holes could be linked to the regulation of star formation in galaxies, as the energy emitted by the black hole can heat up the surrounding gas, preventing it from collapsing and forming new stars. The fate of galaxies, merging, colliding, and evolving. The evolution of galaxies is a continual process. As galaxies merge and evolve, their structures change, and new stars are born while others die. Over billions of years, galaxies will continue to interact with one another, forming even larger structures and leaving behind remnants such as elliptical galaxies and supermassive black holes. In the distant future, our own Milky Way galaxy will collide with the nearby Andromeda galaxy. This galactic collision will reshape both galaxies, eventually leading to the formation of a larger elliptical galaxy. The outcome of this collision will depend on the amount of gas in each galaxy and how it interacts with the newly formed structure. Conclusion: Galaxies as cosmic architects. Galaxies are the fundamental building blocks of the universe. From their birth in the early universe to their continued evolution through mergers and interactions, galaxies play a central role in shaping the cosmos. The study of galaxies helps us understand the larger structure of the universe and provides insights into the forces of gravity, dark matter, and radiation that govern the cosmos. As the universe continues to evolve, galaxies will continue to form, merge, and evolve, creating a dynamic and ever-changing cosmos. The process of galaxy formation is a cosmic dance, driven by the forces of gravity and the properties of dark matter, which create the structure and complexity of the universe. Galaxies are not just collections of stars, they are the architects of the universe, shaping the cosmos and determining its future. Stars are the most fundamental and awe-inspiring objects in the universe, playing a crucial role in the creation of light, the formation of elements, and the development of the cosmos as we know it. The birth of a star marks a turning point in the evolution of the universe as it transforms matter and energy into the radiative processes that fuel galaxies and life itself. Understanding how stars are born, how they evolve, and how they die is essential to understanding the universe's past, present, and future. In this chapter, we will explore the process of stellar formation, the factors that determine how stars come into being, and the role of stars in the broader cosmic evolution. We will also discuss how stars create the elements that make up the universe and how they influence the formation of planets and the potential for life. The formation of a star, from gas to nuclear fusion. The process of star formation begins with a molecular cloud, a cold and dense region of gas and dust in space. These clouds are made mostly of hydrogen, the building block of stars, but they also contain trace amounts of heavier elements like carbon, oxygen, and nitrogen, which will later be fused in stars. The gas within these clouds is spread out over vast regions of space, and while it is still too diffuse to form stars by itself, the cloud is prone to collapse under the force of gravity. As the gas in a molecular cloud begins to collapse, it forms clumps or cores where the density increases. These cores are often the birthplaces of new stars. As the gas collapses, it heats up and becomes denser, eventually reaching temperatures high enough to initiate nuclear fusion. This process, called protostar formation, begins when the core temperature of the collapsing gas reaches about 10 million degrees Celsius. At this temperature, nuclear reactions begin, and hydrogen atoms fuse to form helium, releasing enormous amounts of energy in the form of light and heat. At this point, the protostar enters a phase in which it is not yet a fully fledged star, but is still accumulating mass from the surrounding gas and dust. The energy generated by the fusion reactions causes the gas surrounding the protostar to push back, balancing the inward force of gravity. This delicate equilibrium is what allows the star to form and stabilize. The role of gravity in star formation. Gravity is the driving force behind the formation of stars. It is responsible for the collapse of gas clouds, the heating of the gas as it condenses, and the eventual initiation of nuclear fusion in the core of the star. In the early stages of star formation, gravity causes the cloud of gas to collapse inward, increasing the density and temperature. As the gas condenses into smaller and smaller regions, the pressure inside the cloud increases, which further accelerates the collapse. Eventually, the material in the cloud will form dense cores, and as the temperature rises, the central region will begin to glow, marking the birth of a protostar. During this phase, the protoplanetary disk forms around the protostar, where dust and gas can come together to form planets and other celestial bodies. Gravity not only pulls material toward the star, but also helps create stellar winds, which are outflows of hot gas from the star's surface. These winds blow away the remaining gas and dust, clearing the area around the star and allowing it to shine brightly. Nuclear fusion, the heart of a star. Once a star has reached a sufficiently high temperature and pressure, nuclear fusion begins in its core. Nuclear fusion is the process by which atomic nuclei combine to form heavier elements, releasing large amounts of energy in the form of light and heat. The most common fusion reaction in a star's core is the fusion of hydrogen nuclei, protons, into helium, which releases an enormous amount of energy. The energy produced by nuclear fusion creates the outward pressure that balances the inward pull of gravity, keeping the star stable. This balance, known as hydrostatic equilibrium, ensures that the star does not collapse under its own gravity or blow apart due to the pressure of its own fusion reactions. The temperature in the core of the star is typically around 10 to 15 million degrees Celsius, hot enough to sustain the fusion of hydrogen into helium. As stars continue to burn hydrogen in their cores, they generate light and heat, which makes them visible to us. Over time, the core of the star will eventually run out of hydrogen, causing it to expand and enter the next phase of its life cycle. Stellar evolution, from main sequence to death. A star's life is not static. It evolves over millions to billions of years, depending on its size. The process of stellar evolution is primarily determined by a star's mass. Low-mass stars, less than about 8 times the mass of the Sun, and high-mass stars, greater than 8 times the mass of the Sun, have very different life paths and endings. The main sequence, a star's longest phase. Most stars, including our Sun, spend the majority of their lives on the main sequence of the Hertzsprung-Russell diagram, a plot that shows the relationship between a star's temperature and luminosity. During the main sequence phase, a star fuses hydrogen into helium in its core, producing energy and maintaining hydrostatic equilibrium. For stars like the Sun, this phase can last for about 10 billion years. In the main sequence phase, the star remains relatively stable, burning hydrogen at a constant rate. The balance between the inward pull of gravity and the outward push of energy from fusion keeps the star stable. Over time, however, as the hydrogen in the core is depleted, the star will begin to evolve. The red giant phase, the end of hydrogen fusion. As a star's core runs out of hydrogen, the core contracts and heats up, while the outer layers of the star expand. This expansion causes the star to become a red giant. In the red giant phase, the core temperature rises enough to fuse helium into carbon and oxygen, while the outer layers of the star continue to expand. The star's outer envelope can expand to several times the size of its original radius, and the star becomes much more luminous, though its surface temperature drops, giving it a reddish appearance. For low-mass stars like the Sun, this is the penultimate phase in their evolution. Once the star has exhausted its helium fuel, it will shed its outer layers, forming a planetary nebula, while the core becomes a white dwarf, a dense, non-fusing remnant of the star. For high-mass stars, the process is much more violent. The supernova, the death of a high-mass star. High-mass stars, greater than 8 times the mass of the Sun, follow a very different evolutionary path. When a high-mass star exhausts its helium fuel, it begins to fuse heavier elements, eventually creating an iron core. Unlike hydrogen and helium fusion, the fusion of iron does not produce energy, and the star can no longer maintain hydrostatic equilibrium. The core collapses under the force of gravity, and the outer layers of the star explode in a supernova. A supernova is one of the most violent events in the universe, releasing an enormous amount of energy. The explosion creates a shockwave that can trigger the formation of new stars in nearby gas clouds. The elements created in the explosion, such as gold, platinum, and uranium, are scattered into space, enriching the interstellar medium with heavier elements that will eventually form new stars, planets, and other celestial bodies. After the explosion, the core of the star becomes either a neutron star or, if the mass is large enough, a black hole, regions of space where gravity is so strong that not even light can escape. Stellar nucleosynthesis, creating the elements of life. The process of stellar nucleosynthesis is the mechanism by which stars create the elements that make up the universe. In addition to hydrogen and helium, stars produce a wide range of elements through nuclear fusion. These elements are then scattered into the universe when stars die, enriching the interstellar medium and making it possible for new stars, planets, and even life to form. For example, elements like carbon, nitrogen, and oxygen, key ingredients for life, are created in the cores of stars and spread throughout the universe during supernova explosions. These elements then become part of new stars and planets, allowing for the formation of Earth-like conditions and the possibility of life. The cycle of star birth and death. Stars are not permanent fixtures in the universe. They are born, evolve, and eventually die, and their death plays a crucial role in the evolution of the cosmos. The birth and death of stars create the elements that make up planets and life, while their gravitational influence shapes galaxies and large-scale structures. The cycle of star birth, life, and death is a key component of the universe's dynamic, ever-changing nature. Stars also play an essential role in the dark matter and dark energy that shape the universe's evolution. Their gravitational pull influences the formation of galaxies, and their deaths release vast amounts of energy and matter that will continue to shape the universe for billions of years to come. Conclusion: the heart of the universe. Stars as cosmic engines. Stars are the heart of the universe, driving its evolution and shaping its structure. Through the processes of nuclear fusion and stellar nucleosynthesis, stars create the building blocks of matter, fueling the formation of galaxies, planets, and life. From their birth in molecular clouds to their death in supernovae and the creation of black holes or white dwarfs, stars represent the energy and creativity of the cosmos. As we continue to explore the universe, the study of stars will remain at the forefront of cosmology, as they are the engines that drive the dynamic processes of the universe and provide the foundation for everything we observe today. Stars are not eternal. While they shine brightly and fuel the universe with energy and light, every star eventually reaches the end of its life cycle. When a star dies, it releases vast amounts of energy and material, contributing to the chemical evolution of the universe. The death of stars is one of the most dramatic and important events in the cosmos, driving the creation of heavy elements, the formation of black holes, and the continuing development of galaxies and other cosmic structures. In this chapter, we will explore the processes of stellar death, including supernova explosions, the formation of white dwarfs, neutron stars, and black holes, and how these cosmic events contribute to the chemical enrichment of the universe. We will also discuss the role of stellar death in the creation of the elements essential for life and the formation of the universe's most mysterious objects. Black holes, the end of a star's life. The death of low and high-mass stars. A star's death is determined largely by its mass. Stars of different sizes go through different processes at the end of their lives, and the manner in which they die has significant consequences for the universe. While all stars eventually exhaust their nuclear fuel, the way they die and what happens afterward varies dramatically based on their initial mass. The death of low-mass stars, white dwarfs. Low-mass stars, like our Sun, go through a red giant phase as they begin to exhaust the hydrogen in their cores. In this phase, the star expands, and its outer layers are blown off, creating a planetary nebula. The core of the star, however, is not massive enough to undergo the collapse that leads to a supernova. Instead, it remains as a white dwarf, a dense Earth-sized remnant of the star that no longer undergoes fusion. A white dwarf is made mostly of carbon and oxygen, the products of helium fusion in the star's later stages. Over billions of years, a white dwarf will gradually cool and fade, becoming a cold, dark remnant in the universe. Despite being small, white dwarfs are incredibly dense. Typically, a teaspoon of white dwarf material would weigh around a ton on Earth. While white dwarfs no longer shine through fusion, they can still emit faint residual heat for billions of years before cooling to near absolute zero. The death of high-mass stars, supernovae stars much larger than the Sun, more than 8 times its mass, follow a very different path. When a high-mass star exhausts its hydrogen and helium fuel, it begins to fuse heavier elements in its core. This process continues until the core forms an iron nucleus, at which point the star can no longer produce the energy needed to counteract the inward pull of gravity. As a result, the core collapses under its own immense gravity, causing a supernova explosion. Wow! Supernova is one of the most powerful events in the universe. The explosion releases an enormous amount of energy, briefly outshining an entire galaxy. The outer layers of the star are ejected into space at velocities of up to 10,000 km/h, enriching the surrounding interstellar medium with heavier elements like iron, nickel, and gold. This process is called nucleosynthesis and is responsible for the creation of many of the elements that make up planets, stars, and life itself. After a supernova, the core that remains can become either a neutron star or, if the star is massive enough, a black hole. Neutron stars, the collapsing remnant of a star. A neutron star is the remnant of a high-mass star after a supernova explosion, and it represents one of the most dense objects in the universe. The collapse of the star's core causes the protons and electrons to combine, forming neutrons. This results in a star composed almost entirely of neutrons, which are tightly packed together under extreme pressure. The density of a neutron star is so high that a single cubic centimeter could weigh as much as 400 million tons on Earth. Neutron stars are typically only 10 to 20 kilometers in diameter, but they have a mass between 1.4 to 2 times the mass of the Sun. Neutron stars are incredibly hot when they first form, and they emit intense radiation, including X-rays and gamma rays. Some neutron stars also exhibit powerful magnetic fields and rapid rotations, spinning several times per second. These objects are often observed as pulsars, emitting regular beams of radiation, which we detect as pulses of light. Black holes, the most mysterious objects in the universe. If a star's core is massive enough, more than 3 times the mass of the Sun, the collapse will continue, eventually leading to the formation of a black hole. Black holes are regions of space where gravity is so strong that not even light can escape, creating a point of no return known as the event horizon. At the center of a black hole lies a singularity, a point of infinite density, where all the matter that collapsed into the black hole is compressed. The event horizon marks the boundary beyond which nothing, not even light, can escape. The gravitational pull near a black hole is so intense that time slows down for objects near the event horizon, a phenomenon known as gravitational time dilation. The formation of black holes is closely tied to the collapse of massive stars, and their presence plays a significant role in the evolution of galaxies. Many galaxies, including our own Milky Way, contain supermassive black holes at their centers, with masses millions to billions of times that of the Sun. These supermassive black holes likely formed from the merger of smaller black holes over time and have a profound impact on the dynamics of their host galaxies. Stellar nucleosynthesis, the creation of the elements. One of the most important outcomes of a star's death is the creation and distribution of the elements in the universe. During a star's lifetime, it fuses hydrogen and helium into heavier elements in its core. The heaviest elements, such as iron, nickel, and gold, are created during a supernova explosion. When a star dies in a supernova, it releases these heavy elements into space, enriching the interstellar medium and providing the building blocks for the next generation of stars, planets, and even life. These elements are critical for the formation of rocky planets like Earth and for the chemistry that underpins life itself. The process of stellar nucleosynthesis is responsible for creating nearly all of the elements heavier than hydrogen and helium. Elements like carbon, oxygen, nitrogen, and iron are all formed in the cores of stars and spread throughout the universe when those stars die. The complex chemistry that leads to the formation of life is made possible by the elements created in stars, and every atom in our body can trace its origins to the fusion reactions that took place in stars billions of years ago. The role of supernovae in galaxy evolution. Supernovae are not just important for creating the elements that make up stars and planets, they also play a significant role in shaping the evolution of galaxies. The explosion of a supernova releases enormous amounts of energy into the surrounding space, creating shock waves that can trigger the formation of new stars in nearby gas clouds. These shock waves also help to disperse the heavy elements produced by the supernova, enriching the interstellar medium and creating the material for future generations of stars and planets. In some cases, supernovae can also play a role in galaxy evolution. The energy released by multiple supernovae in a galaxy can blow away large amounts of gas and dust, inhibiting future star formation and causing the galaxy to evolve into an elliptical galaxy, a galaxy with little new star formation. On the other hand, the material expelled during supernovae can also help form new stars, contributing to the ongoing evolution of spiral galaxies like our Milky Way. The importance of stellar deaths in cosmic evolution. The death of stars is an essential part of the cosmic cycle of creation and destruction. Stars are the factories that produce the elements essential for life, and their deaths release those elements into the universe, enriching the interstellar medium and paving the way for the next generation of stars and planets. Stellar deaths are also responsible for the creation of the most extreme objects in the universe, including neutron stars and black holes. Without the deaths of stars, the universe would not have the elements needed for life or the complex structures that make up galaxies, star systems, and planetary bodies. Stellar deaths are the mechanism by which the universe continues to evolve, creating the conditions for life and shaping the cosmos in an ongoing cycle of birth, death, and rebirth. Conclusion: the cosmic cycle of life and death. Stars are the lifeblood of the universe. They are born, live, and die, creating the elements that form the building blocks of planets, life, and everything we know. The death of stars, whether as white dwarfs, neutron stars, supernovae, or black holes, is a fundamental part of the universe's evolution. It is through this cycle of stellar birth and death that the universe becomes more complex and rich in elements, eventually allowing for the formation of planets and the possibility of life. In the next chapter, we will delve into how the birth and death of stars contribute to the formation of planetary systems, how the solar system formed, and how stars and their planetary systems evolve over time. The death of stars plays a vital role in the formation of new elements and the creation of cosmic structures. But beyond the birth and death of stars lies another crucial process, the formation of planetary systems. Planetary systems, like our own solar system, are the results of complex processes where dust, gas, and debris are drawn together by gravity, eventually forming planets, moons, and other celestial bodies. Understanding how planetary systems form and evolve gives us insight into the birth of new worlds and the conditions necessary for life to arise. In this chapter, we will explore the process of planetary system formation, beginning with the role of molecular clouds in shaping new star systems. We will also examine the protoplanetary disk, where planets are born, and discuss how gas giants and rocky planets form. Lastly, we will consider the potential for life elsewhere in the universe and how planetary systems provide the ideal environments for the conditions necessary for life. Molecular clouds, the birthplaces of planetary systems. Planetary systems are born in the cold, dense regions of space known as molecular clouds. These clouds are primarily made up of hydrogen and helium, with trace amounts of heavier elements like carbon, oxygen, and nitrogen. They are also known as stellar nurseries because they provide the conditions necessary for star formation. Within these molecular clouds, gas and dust particles are spread out over vast distances. However, gravity eventually causes these particles to clump together, forming dense regions known as clumps or cores. These cores contain the building blocks for stars and planets. As the core collapses, it heats up, and when it reaches a critical temperature, nuclear fusion begins in the center, giving birth to a protostar. But the process doesn't stop there. Around the newly forming star, a protoplanetary disk begins to take shape, a rotating disk of gas and dust that surrounds the star and becomes the birthplace of planets. The protoplanetary disk, the birthplace of planets. The protoplanetary disk is a critical stage in the formation of planetary systems. As a protostar forms, the gas surrounding it begins to condense into a rotating disk due to the conservation of angular momentum. This disk is composed primarily of hydrogen, helium, and dust particles, which eventually give rise to the planets, moons, and other objects in the planetary system. In the outer regions of the disk, where temperatures are lower, heavier elements such as metals and silicates begin to condense into solid particles. These particles collide and stick together, forming larger bodies known as planetesimals, the building blocks of planets. Meanwhile, in the inner regions of the disk, where temperatures are higher, gas giants like Jupiter and Saturn begin to form by accumulating massive amounts of gas. Over millions of years, these planetesimals continue to collide, merge, and grow, eventually forming protoplanets, larger bodies that are on the way to becoming full-fledged planets. The interaction between these protoplanets and the gas in the disk leads to the formation of planets, moons, and other objects like asteroids and comets. The formation of gas giants and rocky planets. The process by which planets form in a protoplanetary disk depends largely on the distance from the central star and the amount of material available. In the outer regions of the disk, where temperatures are low, gas giants like Jupiter and Saturn are able to form. These planets start by accreting gas from the surrounding disk, growing to immense sizes. Gas giants are made mostly of hydrogen and helium, with solid cores composed of metals and ices. In contrast, the inner regions of the disk are too warm for gas giants to form easily. Here, only the rocky planets like Earth, Venus, and Mars can form. These planets are composed mainly of silicates and metals, as only these materials can condense in the heat of the inner solar system. The process of accretion in the inner disk is slower, as there is less material available, but the formation of terrestrial planets is still possible. While the gas giants are massive, they are much less dense than the rocky planets because they are made mostly of light gases. The rocky planets, on the other hand, are denser as they are made of heavier materials. Over time, the material in the protoplanetary disk is depleted, and the remaining gas is blown away by the solar wind of the newly formed star. The role of migration. Planetary systems evolving. Over time. Once the planets have formed, they are not static. In many cases, planets undergo a process called planetary migration, where their orbits change due to gravitational interactions with other objects in the system, including other planets, planetesimals, and the protoplanetary disk. Planetary migration is thought to have played a major role in the evolution of our own solar system. For example, early in the solar system's history, Jupiter and Saturn may have migrated inward, disrupting the orbits of smaller objects and causing the scattering of gas and debris. This migration likely had a significant impact on the distribution of planets in the solar system and could have contributed to the formation of the asteroid belt and the eventual placement of the outer gas giants and inner rocky planets. In some cases, planetary migration could have led to the ejection of planets from the system or the collisions of planets in different orbits. Such interactions could have had profound effects on the evolution of the planetary system, potentially causing the formation of new moons or altering the orbits of planets over time. The role of giant impacts, shaping the planets. One of the most significant events in the early history of any planetary system is the occurrence of giant impacts, collisions between protoplanets and planetesimals. These impacts were common in the early solar system and played a major role in the formation of planets and moons. For example, it is widely believed that the moon formed as a result of a giant impact between the young Earth and a Mars-sized body known as Theia. The collision caused a significant amount of debris to be ejected into orbit around the Earth, eventually coalescing to form the moon. Such giant impacts can also lead to the formation of planetary rings and the creation of unique surface features on planets, like the large craters on Mercury and the Moon. In addition to affecting the planets themselves, giant impacts can also have a profound effect on a planet's atmosphere and climate. These collisions can release vast amounts of energy, causing temperature fluctuations and triggering the formation of volcanic activity. The effects of such impacts can even alter a planet's chemical composition, influencing the potential for life to evolve. The role of volatile elements, water and atmospheres. The presence of volatiles, elements that can exist as liquids or gases at relatively low temperatures, is crucial for the formation of planets that could potentially harbor life. Water, in particular, is a key volatile that plays a critical role in shaping a planet's atmosphere and climate. In the inner solar system, the presence of water is largely determined by the amount of water ice in the protoplanetary disk. In the outer regions, where temperatures are low, water ice can condense and contribute to the formation of moons and comets. As planets form, the presence of water, whether in the form of oceans, clouds, or ice caps, is essential for creating the conditions necessary for life. The atmosphere of a planet also plays an important role in its ability to support life. For example, the Earth's atmosphere is composed of a mixture of gases, including nitrogen, oxygen, and carbon dioxide, which helps regulate the planet's temperature and protects it from harmful radiation. The presence of a stable atmosphere and liquid water is often considered to be one of the primary criteria for a planet to be considered habitable. Conclusion: the birth of worlds, the formation of planets and life. The formation of planetary systems is a complex and dynamic process driven by the forces of gravity, accretion, and migration. From the birth of stars in molecular clouds to the creation of gas giants and rocky planets, planetary systems evolve over millions of years. The process of giant impacts and the presence of volatile elements like water are also key to creating the conditions necessary for life. The study of planetary system formation helps us understand not only the origins of our own solar system, but also the potential for life elsewhere in the universe. As we continue to explore distant stars and exoplanets, we are discovering new planetary systems that may harbor the building blocks of life. In the next chapter, we will delve into the search for habitable planets beyond our solar system and explore the conditions necessary for life to exist on distant worlds.